Hi Huskies, we're going to talk about functions today, and this is the first lesson in the functions unit, and there's some really important building blocks. So this video may be kind of long. I'm going to try to go as quickly as I can. First of all, the goal today is that you can identify when is something a function or not a function, and that you know how to properly use function notation. It's kind of a lot to bite off in one lesson, but it's important. I'm not going to talk about the soda machine problems from the front. Basically, this soda machine is functioning correctly if it's predictable. If you know what's going to come out when you press the button every time, then it's functioning correctly. And we're going to kind of use that as a model, but I don't want to go over all of that because I got a lot to do here in this video. So basically we are asking what makes a relationship a function. And so on the first page, this is what you would answer for E. Every input has exactly one output. That's what makes it predictable, that when you press that button, only one thing is going to come out every time you press it. And yeah, when it was broken, every time they pressed the, like on D, every time she pressed slurp, she got a can of lemon twister. But everybody did that. So just imagine this broken soda machine that everybody knows is broken. Hey, it's mislabeled. But if you want a can of lemon twister, just press the slurp button. And it's predictable. So it's still functioning correctly. Now, when it's not functioning correctly is when you press the button and you think you're going to get something and something else comes out, and then the next person comes along, presses the same button, and they get something totally different than you did. When it's not predictable, that's when it's not a function. So we have a few different ways to represent a relationship. You guys have talked about most of these. You should be familiar with ordered pairs. Yeah, you've been plotting points for a long time. Sometimes those are functions. You know what a table looks like. Sometimes those are functions. You know what graphs look like. Many times that can represent a function. Mapping may be new today, and we will show you what that looks like. Kind of a little jelly bean diagram sometimes. And then equations can be functions. And so most of these things you're already familiar with. So don't freak out. You've seen most of this stuff before. I don't know if you've talked about domain and range before. It tends to be something that people haven't remembered from one year to the next, so I'm just going to teach it to you like you don't know. Domain is the set of x's that you use in a function, and the y's, or in a relationship, doesn't even have to be a function, the y's make up the range. So if you can't ever remember which one's the domain, which one's the range, well, then just think of the song Home on the Range, but put in y. Why is the range? I don't know. Come up with something else if you don't like my song. But remember this. You have to know that the domain is the x's and the range is the y's. Okay, what we're going to do to answer 2, 3, 4, 5, and 6 on the back of your paper is to do this by example and non-example. So you're just going to stop the video for a second, pause it, stare at this. I'm telling you the stuff on the left is a function, stuff on the right is not a function. We're going to start with ordered pairs. You've seen a bunch of points before. When you have just a list of points, sometimes they're a function and sometimes they're not. Now, I want you to stop it and think about it for a while, but I'm not going to take the time to do that on my video because I don't want it to be 2 hours long. So I'm going to just assume that you've stopped it, stared at it, come up with what's different. So what makes this thing a function or not? Well, let's look on the not function side. On the not function side, remember that the left, the x's, those are our domain. That's the input. So this is like the button you press on the soda machine. So this is kind of like a shorthand way of saying what happened when I pressed buttons on the soda machine. Well, I pressed button 1 and I got this kind of soda out. And that's my range. Y's are green. And then somebody else came and pressed the button 2 and they got this soda out. Then somebody else came and they pressed the 1 button again. But they got this soda out. Oh, that's not consistent or predictable. First I pressed a 1 and I got a 1 over here. Then I pressed a 1 and I got a 3. What the? That's broken. That's not a function. So in other words, what you're looking for is a repeated x that goes to two different y's. Repeated x's going to two different y's. Like if I just accidentally wrote the same point twice, that's okay, but two y's. Different y's. So look at the one below that. Again, we have here's an 8 and here's an 8, but the first time I get a 17 and the second time I get a 19. That is not a function because I have that X button that's giving me two different sodas when I press it. So look back over here at the side that is a function. Okay, I pressed button 1, I got soda 2. I pressed button 2, I got soda 2. I pressed button 3, I got soda 3. Yeah, that's kind of a boring function, but it is. It's a function because none of the X's, none of the buttons gave me two different sodas. But now you say down here, well, look, I pressed button 17 and I got out an 8. And then I pressed button 18 and I got out an 8. And I pressed button 19 and I got out an 8. Hey, haven't you ever seen a Coke machine with two buttons to press for a Coke? That's okay. That still works. Another way I like to think about this is using soccer moms. So let's say that the soccer moms are the X's. Moms are the X's. Right here. So I have mom 17, and I have mom 18, and I have mom 19. And the Y values, the range, is the range of activities their children do. So up here, like soccer mom 1 went to their first kids game. Soccer mom 2 went to maybe a ballet recital. Soccer mom 3 went to a flag football game. You see what I'm saying? They went to different activities. But down here in this second example, all these moms went to the same soccer game. Hey, are you allowed to do that? Sure, maybe they're friends, 17, 18, and 19. They're going to hang out and visit while their kids play soccer. They're all at the same soccer game. That's totally appropriate. But on this one on the right, if this is our soccer mom, she's trying to go two different places. She's trying to go to game 17 and a ballet recital at the same time. She can't do that. She cannot be in the same place, two different places at the same time. So that's how, it's not a function, because that mom is not functioning correctly if she has to be in two different places at the same time. So just remember the moms are the domain and the Y's the range. That's the range of activities their kids do. That's just a kind of a real life example to help you think about this. Okay, when is a table a function? When is a table not a function? Let's see. Well, we've kind of already talked about this idea of the soccer mom going to two different places at once. So let's look at that again. Like X's, do we have any moms that are repeated? Oh, look, here are two zeros. This is mom 0, and she is trying to go to -12 and 500 at the same time. Or if you want to think about it like the soda machine, then you press the 0 button, and first you got a soda out that was a -12. Then you press the 0 button and you got a soda out that was a 500. That's not consistent. That's not predictable. Who knows what's going to come out next? So that's why that's not a function. And you're right. -1 also is trying to go two different places. So, hey, it's broken on many levels. So that's why that's not a function, because, again, I have repeated X's going to two different Y's. And so when is a table not a function? You got to write that down for number 3. When you've got this repeated X idea, when it's going to two different Y's or many different Y's. So watch out for those repeated X's. Notice over here on the left, those X's are all different. On this table that I've written horizontally, those X's are all different. But this table down here, well, I've got 3 1s. First, when you press the 1 button, you get a 30. Then you press the 1 button, you got a 50. Then you press the 1 button, you got 120. Your soda machine is broken. That is not functioning correctly because you have no idea what comes out when you press a 1. Could be anything. Same idea with the 2s. Okay, this is a little bit different. How can we tell just by looking at a graph if it's a function or not? Well, let's look at this one down here. This is just a set of dots. But remember that the dots each represent an ordered pair. So what if I were to list those out like in ordered pairs? I don't know. Let's just pretend we know what the measures are. Maybe this is like over 3, up, 1, 2, 3, 4, or something, 3, 4. What would the next one down be? It would be over 3, up, I don't know, 2 maybe, and then we'd have over 3, up 1, over 3, down 1. I don't have room to write it on here. It would be over 3, down 3, or something like that. Well, hey, look at what's going on. All of these, that's the same soccer mom, and she's got 5 kids doing stuff at exactly the same time. She can't be at the football game, the orchestra concert, the ballet recital, the chess tournament. She cannot go to all those places at the same time. She would not be functioning correctly. Or soda machine, example, if you press button 3, you got out soda 4. Then you press button 3, you got out soda 2. Then you press button 3, you got out soda 1. Then you press button 3 and you got out -1. Hey, next time you press button 3, what the heck's going to come out? I have no idea. Your machine is broken. So that's what it would look like. But you know what? The great thing about graphs is you don't have to go through that whole process. I'm just kind of trying to show you how it's an analog of the ordered pairs. But a faster way to tell on a graph is to look for the vertical line test. So if it passes the vertical line test, then it's a function. And I'm just writing it down before I even show you what it is. But if it's a function, it will pass the vertical line test. If it's not a function, guess what? It's going to fail the vertical line test. So what's a vertical line? That's going straight up and down. I'm going to draw some vertical lines on here. There's a vertical line, there's a vertical line, there's a vertical line. Here's some more. Remember, these are all failing because we already know these are not functions. Here's a vertical line. What happened when I drew those vertical lines? They were intersecting my function in at least 2 places. This one intersected it 5 times. This one had 2 places. If I were to draw vertical lines over on the side of our screen that we know they are functions, one time, anywhere I draw a vertical line, it's only going through my function 1 time. Let's check out these dots. Yeah, okay, right, yes. In other words, every time I press the X button, I'm only getting 1 predictable Y value out. I don't have this sad situation with the soccer mom trying to divide herself into 5 pieces so she can go to all these activities. So that's what the vertical line test looks like. You draw a vertical line and you see if it goes through the graph more than once. If it goes through the function more than once. That's how you can tell on a graph quickly. So, we love to decide if a graph is a function because boom, draw just lines on there, check it out. So great. This is a mapping. Now, this looks like a lot of stuff and it's kind of overwhelming, but just pause for a second. A mapping is when you just have a list of numbers and you kind of draw a circle around them or a square or a jelly bean shape and you just say, hey, that's my domain. This list of numbers over here in the circle is my domain, and this list of numbers over here on the right, that's my range. Domain is usually on the left, and the range is usually on the right. But how do we know what the function is? Well, those are the arrows. The arrows are telling you what the relationship is. So over here, I'm going to just try to point to all these things. Over here, we've got that we have a domain, is the stuff on the left. My range is the stuff on the right. And I've labeled them with a D and an R. Now, in this function, 8 goes to 6, 9 goes to 14, 10 goes to 10, 11 goes to 18, and 12 goes to 14. That's just one way of writing this. If I wanted to write this instead as like ordered pairs, I could write this list of ordered pairs that would look more like when I pressed the 8 button, I got out a 6. When I pressed the 9 button, I got out the 14. when I pressed the 10 button, I got out a 10. You can write these functions in many different representations for each function. I could now graph these points. I could plot all these points on my graph, and I could see if it passes the vertical line test. So again, it's just another way of writing your function, a mapping. This is what it would look like if we just grouped. It's kind of like we just took all the x's and we lumped them together into one area. Hey, that's my domain. And then we took all these y's and just lumped them together. Hey, look at that. 2 different things are going to 14. Is that okay? Hey, can 2 moms go to the same soccer game? Yes. Can 2 different buttons on a machine give me a Coke? Yes, they can. So that's fine. That's still a function. So now let's look over here at the not function side. How can you tell when a mapping is not a function? Well, this is my red flag. This 12. This poor mom is trying to go 2 different places at once. Or I pressed the 12 button and I got a soda. Then I pressed the 12 button again and got a different soda. That is not functioning correctly. The 11 is also not functioning correctly. So again, it's the idea of looking for x's that go to 2 different y's. That's when something is not a function. An x goes to 2 places. But wait, look at the function the relation is not a function. Look at the one below it. None of the x's are going 2 places, but you said that's not a function. So why is this not a function? Well, if this was a soda machine, and I press the 0 button down here, what soda is coming out? I don't know. Nothing. It's not going somewhere. If you can remember back to when we defined what a function was, let's see, right here. Every input has exactly one output. If there's a button on that machine, I better get a soda out when I press it. Whoops. So this 0, this is not a function. This soda machine is not functioning correctly because when I press a 0, nothing comes out of the machine. It just steals my money. So it doesn't have exactly one output. It doesn't have an output at all. So that's kind of what makes that not a function. So you could write down must have x must have exactly one output. Every x has to have an output. X must have exactly one output. Okay. So let's just super quickly talk about equations that are functions and not. We are not going to do this in class. This is just kind of a peek ahead at something that you'll have to do in later years. Equations that are not functions would be equations that if you graph them, they would fail the vertical line test. And you don't know what a lot of these look like, so you have to just kind of take my word for it. But you do know how to graph that one. That is the vertical line that goes through 5, like that. And does that fail the vertical line test? Yeah, because it goes through an infinite number of times. Vertical lines are not functions. So if I had over here, if I were to graph 3x minus 5, it'd be down here, and my slope up 3 over 1, it would just be this line that's slanted, and that passes the vertical line test. That's not bad at all. Okay, so you can notice on here that when your y has an even number for the exponent, that's what's going to make it not a function. This is actually, the graph of this is like a sideways U-shaped thing that fails the vertical line test. Oh, it actually even goes that way. Doesn't really matter. Well, hey, here's an even exponent. Yeah, but those are okay because those are on the x. And so that just means that if I were to graph that, it would be an up and down u, and that still passes the vertical line test. This is 2 x's going to the same y, 2 moms going to the same soccer game, 2 different buttons giving me the same drink. That's okay. Hey, what does y equals 5 look like? Horizontal line. That passes with flying colors. Okay, remember, the domain is the set of the x's and the range is the set of y's. We're still kind of a long ways from being able to do your homework because we have just been able to now recognize when something is a function or not. And so why is the range? Well, a lot of times you're going to be asked to write the domain and write the range. So we got to practice doing that. How do you write the domain? Well, this is not on your classwork. This is just a table that I copied off of something else, but it's going to help us practice how to write the domain. And this is kind of a simplified version. I don't want you to do the super technical version of it. I'm just going to simplify it, and I just would like you to write it in curly brackets, braces. I don't know really what the names of those are. But for me, in my class, I would like you to write the domain, give me the D for domain equals, and then we're going to use set builder notation that's simplified a little bit. Just list everything in those curly braces. And yeah, I'm looking for those braces, those curly brackets. So what is the domain of this function that is written as a table? Well, I don't know if you can read this. This says n, and this says f of n. Now, we talked about that function notation way back when we did sequences, and we didn't really explain a lot about what it means. And I'm going to explain it in this video, but just not right now, at the end. So for now, all you need to know is that the domain, the domain is the stuff on the left, and the range is the stuff on the right. So the domain is the set of numbers that are being used for the x's. Well, there's no x's on this one. Well, it's n, x, w, whatever variable. That's how I'd write my domain. I would just use the curly brackets, and I would just put the numbers in a row. That's it. Hey, how do I write the range then? Well, the range for this table, this set of points that are in a table, the range is the set of y's such that y is 5, 11, and 13. The very formal way to write that is, like I said it out loud, the set of y's such that y equals 5, 11, commas, and 13. I'm not making you do this whole y such that y equals. I'm not. I've after teaching this for so many years, I just have simplified this enough that, hey, if you can figure out that the domain is the input and the range is the output, and you can get it in the curly braces, that's good enough for me for now. Let's do number 7. This is what you're going to have to do on your homework. This is like the back of your homework. So if you're here for help on your homework, this is what you need help with. 7a says, examine the relations. First of all, state the domain, then state the range, then decide if it's a function, yes or no. Okay, the domain. Domain is, in curly brackets, just list all the numbers that you see. Wait, I already have a 2. Don't list the 2 twice. See that 2? Once is enough. And then we have a 9. So it's bad to repeat the numbers in your domain. Don't do that. Now, I just wrote them down in the order that I saw them, but it kind of is a little bit better manners if you were to actually write them in ascending order from least to greatest. So that would be like -1, 0, 1, 2, 3, and 9. Now, there's always a danger when you do that you skip a number, you leave it out or whatever. So I'm going to be okay if you don't put them in order from least to greatest, but technically you probably should. So range is the set of y's, and that's just your outputs. So what are the outputs that I've got here? 4, -5, 9, 7. I already had 4, so I don't need to write it again. And 2. That's my range. And of course, you could write that in order. Now, is this a function? Well, I already have this soccer mom here trying to go to game 9 and ballet recital -8 at the same time. And so that is not a function. I saw this red flag of the 2 different x's that are being repeated. That's how you do 7. Let's do that for your mapping on B. Well, the domain is super nice on this one because, hey, it's already given. The domain is just -2, -1. That is a negative, dang it. 0, 1, and 2. Done. It's already even in order. How nice was that? And then my range was 4, 6, and 8. well, why is my range so much smaller than my domain? Well, a couple of these went to the same game. Those two moms went to game 4, and these two moms went to this recital. So, is that okay? Is that a function? Yep. That's a function. Because the each mom is not trying to be in two places at once. So on C, when I just give you the dots like this, a lot of times that is kind of hard for kids to see. If it's not hard for you to see it at this point, awesome, go ahead and write the domain. What might help you, though, is to write them out as points. Hey, what's the location of this? What's the ordered pair that goes with that point? It's at -3, 1. Okay, how about this point? That is at -2, 3. And then, let's see, this is the one that shows up next, -1, -1. So by just writing these as ordered pairs, it'll be a lot easier for you to see what's my domain, what's my range. The next one is at 2, 3. And the last one over here is at 3, -2. Okay, so if I were going to write my domain, that would just be all the x's. That's going to be all the numbers in the first part of that ordered pair. So let's see, I'm running out of room. I'll just do it down here. The domain is -3, -2, -1, 1, 2, and 3. That's just all the set of x's, the first numbers in each of those ordered pairs. And then my y's would be my range. So that's going to be the second set of numbers in my ordered pairs. And some of them are the same, and that's okay. -1, oh, I forgot -2 if I was going in order, and 1 and 3. And that's okay. You can have the same, because does this pass the vertical line test? You betcha. This does not pass the horizontal line test. These two went to the same, and these two went to the same, but that's okay. That's just two moms going to the same soccer game. It's not a one-to-one function, but hey, you don't have to know about that right now. So just the fact that it passes the vertical line test is enough. It's a function. All right, now your domain and range on this are going to be a little bit trickier. And this is kind of the weird sort of problem that shows up on your homework. So first of all, the domain. The domain is a set of x's. So I like to turn my pencil to be a vertical line and say, well, am I using any x's over here? Have I started using any x's? No, 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 no. Boom. Right there is the first time my function shows up. What is the x value of that point right there? Well, -1, -2, -3, -4. The location of this point right here, we could write it as an ordered pair, would be -4, 3. Whoops, 3. So my domain starts using x's when I get to -4. That was my first one. Well, then I don't have points anymore, though. Am I using -3.8, -3.7, -3.5, -3, -2.9? I'm using all these x's. All these x values right here do have a value on my function, and it's going to keep going forever and ever and ever. So as I go out here, are there still values? Am I going to use the value like x equals 100? Yeah. X equals 1,000? Yeah. 1,000,000? It's just going to keep going forever and ever and ever because of this arrow right here on my function. So that means that I'm starting at -4, but my x's are going to go all the way to infinity. To infinity and not beyond, because there's nothing beyond infinity for us. So that's the inequality that you're going to use to represent the domain here. It's the set of all the x's such that -4 is where I started, and I'm never going to stop. It's going to keep going forever. Okay, let's erase a bunch of stuff here and try to find out what our range is. So you always need to start at the negative side of things. So I turn my pencil to be a horizontal line, like the horizon, right? Am I using a y value down here? Well, yeah, that arrow would have been down there. Am I using a y value way down here? Well, eventually it would have got there. I could keep drawing those lines. I'm using all those y values down there, starting where? This is kind of weird to think about, but it's always existed. It keeps going all the way from negative infinity it started. And so for my range, it's the set of y's such that negative infinity is on the very low end. And where does it stop? Well, I'm using all these y values. Yep. Using all these y values. Hey, there's no more y's. My function has stopped. Where did it stop? It stopped right here at this point. Well, what are the coordinates of that point? We already did that. That was negative 4, 3. The y coordinate of that point is 3. That's the last y value I used. And so I went all the way to 3. Now, I know you're probably confused about the less than. Why is it sometimes less than? Why is it sometimes less than or equal to? First of all, you never use equal to on infinity. Never. You can't ever actually get there. So that means that you can only have a less than or a greater than with infinity. It's never going to get there. It's not a location. It's an idea. You're just going to keep going forever and ever and ever. And since you can't actually ever get to infinity, then you can never use that equals to bar on there. So that's one rule of thumb, that if infinity is involved, it's got to be less than or greater than. And now, because this big solid dot was on our graph, it could actually equal negative 4 and 3. It could have been those values, and so that's why I have the equal to sign underneath there. If you're still confused, I'm going to work out a bunch of examples from your homework, and this is something that maybe just seeing a lot of it will help. Okay, is it a function? Well, I think the best way to tell if a graph is a function is the vertical line test, and this thing passes. So yes, it is a function. I have made a huge mess on the screen. I got to clean it off so we can talk about the ordered pair. Now, the ordered pair should be your friend. You have been seeing ordered pairs since you were in probably 5th grade. So you should be comfortable with those. And you should remember that the domain is the list of all the x's being used. Okay, just write down all the x's from your ordered pairs. And the range. Why is the range? I got a great singing voice at 4:30 in the morning. The list of all the y's, but you only have to list them once. I have a 2 here and another 2 here. You don't have to repeat them. Once is enough. So that's my range. Is it a function? Yes or no? Hey, I don't have any x's being repeated. All of those moms are going to, their soccer games. And mom 1 and 3 ended up at the same game. That's okay. They can visit. That's a function. That mom is not being, stressed out by trying to be at the girls' soccer game and at the boys' orchestra concert at the same time. Okay. It's finally time to talk about function notation. So all year I've just been saying, well, we'll learn about that later. We'll learn about later. Later is now. Yay. Let's say that I wrote down a bunch of equations like this, and I wanted to start talking about them. Well, they're all equal to y because that's how we've been writing equations. Y equals this, y equals that, y equals this. That's fine. That's usually what we do. But it's sort of confusing to talk about, like, how do I mention the third one? You can't see me. I can't even point to it. So I would have to just be like describing, well, the first one is y equals 2x, but the last one is y equals 4x squared. And I would just be talking about it like the first one, the last one, the third one. It could get confusing. And so what mathematicians have decided to do is give them each their own name. And so I could call the first one f. That's the name of that function. Well, sometimes we have functions that have more than one variable in them. And so just to be clear which variable I'm talking about right now, I use that variable in the parentheses. So this is pronounced f of x. And hopefully you remember how we were pronouncing that when we learned about the sequences. And what that means is the function's name is f, and the variable that we're using is x. That's all it means. So I could write that as f of x equals 2x. In other words, you can replace y with f of x anytime you want. But this is where it gets great. You don't have to name the function f. Let's name the second function g. What variable are we using? Still x. So g of x equals 3x plus 1. Let's name the third function h. H. What variable? Still x. Oh, I don't see a variable. That's okay. H of x equals 8. Maybe the x would be 0 in that case, or something like that. Or the slope would be 0. And so it doesn't even really matter if you see an x, well, you just throw in that variable. Well, let's name that fourth function m. M for Mrs. Bagley equals 4x squared. Now, I have not changed anything. I've just replaced all the y's with f of x or g of x or h of x or m of x. This is the moment in school where if you zone out for 10 seconds and you come back, all the y's have disappeared and suddenly we're talking about this goofy thing with the parentheses and what is going on. Anytime you want, you can replace y with f of x, or f of x with y if it's confusing to you. Those mean the same thing. And when I say f of x, I mean whatever letter is used right there. So g of x, h of x, m of x, b of x, all of that. So this is why it's useful, because now I can talk about function g. Function g is linear. Do you know which one I mean? Yeah, you know it's this one because that's the function with the name of g. Hey, function f is also linear because it has a slope 2 and the y-intercept would be 0. Function m is not linear because the x has an exponent on it. It's quadratic. So it's just easier for us to talk about now. I can name them. They have labels to make it easier to talk about. That's all that function notation means. But it's also kind of powerful because it can give us a lot of instructions in a tiny amount of space. So for number 9, I give you a function g of m. This is the function g. What is my variable? It's m. Okay, that's useful information. Function g is 3m minus 5. Sounds kind of linear. It's got a slope. It's got a y-intercept. Yeah, but this is where it gets great. Do you remember back in the day, and I'm pretty sure most of you are good at this, because for some reason everyone remembers what to do when you see this. If I say evaluate, let's say I said evaluate 3m minus 5 when m equals negative 2. Would you know what to do with that? Most of you would. Oh, evaluate this expression, and this is what the variable is. Okay, so I'm going to just take the negative 2 and I'm going to replace the m. So I would get 3 times negative 2 minus 5. 3 times negative 2 is negative 6. Minus 5 is negative 11. Okay, I did it. I evaluated that expression when m is negative 2. All of this stuff that I just said right here can be written in shorthand using function notation, and this is what it looks like. Right there, that tiny little thing where it says g of negative 2 is a faster way of saying all this stuff. Evaluate this expression, 3m minus 5, when m, see how there used to be an m there and now there's a negative 2. Well, I've replaced that variable m with negative 2, so to figure out what it is, I will replace the variable m with negative 2. And then I substitute and I solve, and I got negative 11. That's what you do. So it's just a shorthand. It's an efficient way of giving us the same instructions that you've been seeing for years. Let's do another one. So for part B, g of 4. What does that mean? It means take the function g, which is right here, and replace m with 4. So I can say, well, all right, g of 4 equals 3 times 4 minus 5. I just replaced the variable with that number. But I'm not done. I got to figure out what that is. Now, remember that g is the name of the function. This right here is just a set of instructions. There's nothing to do with that. You don't have to divide by 4. You can't even touch that. Those are the instructions. You're just ignoring the instructions and doing what it says. I've replaced m with 4. So now 3 times 4 is 12. And then I got to subtract 5. 12 minus 5 is 7. So then I could say as my answer, a way of communicating back to somebody, I took the function g, I replaced the variable with 4, and the answer I got out was 7. Now, this is the cool part. This is your input, and this is your output. I put in a 4, and I got out a 7. That means that 4 would have been in my domain, and 7 would have been in my range. Okay, so that's a lot of information in a tiny little space. And it's all stuff that you've seen before. You know how to evaluate expressions. You're good at that. You know how to replace a variable with a number and figure it out. And so you're just communicating back using this function notation as a shorthand. I have done this evaluation, and this is what I got. Okay, another one. We will do C. G of 6. This is instructions. Take the function g, replace the variable with 6. Gotcha. Here's my function g. If I replace the variable with 6, always use parentheses when you substitute, minus 5. So I've just replaced this m right here is now become 6. And then I'm not doing anything with the instructions. That says take the function g and replace the variable with 6. Now let's just do it. 3 times 6 is 18. Minus 5 is 13. And so then you could report back. I took the function g, I replaced the variable with 6, and what I got out was a 13. I put in a 6, I got out a 13. Okay? Now, what the heck is going on with d? G of x? Okay, well, what have we done so far? We took the function g, and we replaced the variable with x. Okay, there's my function g, I replaced the variable with x, and then I figure out what I got. Well, what's 3x minus 5? Trick question, 3x minus 5. So what we could say then is just that g of x equals 3x minus 5. But that looks just like g of m. I know. All I did was replace the variable m with x. So you can see now that the variable I'm using is now x because the function g has an x in it instead of an m. That's it. That's all you do. Okay, I hope that helps with function notation, but never fear, I'll do some more. Whew, such a long video, but this is really important stuff. Okay, now on your homework, we're going to talk about number 15. Hopefully, I've given you enough information that you can handle the first 14 so far. So number 15, the first thing we have to do here is figure out the domain. Turn your pencil vertically like a vertical line, and we are testing it. Hey, am I using any x's over here? No, 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 no. Right. That's when I started using x's at this location. What is that location? It is at -4, -1. That's the location of that point right there. Well, I don't really care about the y value right now. Because I'm doing domain, I am more interested in the x value. So my domain is the set of x's where I started using x's at 4, but these are all decimals and fractions in here. I'm using all my x's constantly until I get that was my last one. Over here, there's no more function. None of those. So what is the last x value that I used? Well, the coordinates of this point right here are 5, -3. And that x value, the last one that I used, was 5. And so I'm using all the x's between -4 and 5. So I hope you remember, I'm just going to move this so it's a little less confusing. I hope you remember when we wrote compound inequalities. I was kind of a jerk, and I kept saying, use the word between, use the word between. Do you see how x is between? X is between -4 and 5. Yeah, we used all the x's that live between -4 and 5. The location of that was 5, -3. We're just ignoring the y values of those points right now because we're not interested in the range yet. We just wanted to know the domain. So that inequality says I'm using all the x's inside here. Now I'm going to kind of erase my little scribbling and show you that it can kind of be drawn like this. This whole section right here is all the x's I was using. All the x's in there started at -4 and I went all the way to 5. That's my domain. Somewhere in there I had a y value for each of those x's. So now let's do the range. The range, y is the range. Well, what y values did I use? So you're going to turn your pencil horizontally like the horizon. And you're going to say, am I using any x values here? No. No. No function exists. No function exists. Boom! Whoa, I missed. Let's try that again. Boom! That's the first time I have encountered my function. You always start on the negative side and move positive. The first time I encountered my function was at this point, 5, -3. Well, since we're doing the range, we're only interested in the y values, so we're ignoring that 5 for a second. What, -3, that's when I started to see some function. And I keep seeing function, keep seeing function, keep seeing function. Yeah, there's still a black line. Whoa, no more. There's no more function. And I'm going to erase these down here because we didn't have function down there. I no longer see function after this point right here. What's the location of that point? It's at -1. Glasses 1, 2, 3, 4. And again, since we're doing range, the y values, we're not really interested in the -1. That doesn't really help us to do anything with, we don't care about the -1, but we do care about how high up these y values go. So you can see by my shading that I have shaded all the y's between -3 and 4. All of the y values between -3 and 4. Because y is the range. I got to use a y when I write the domain. I mean the range. Y in the range. So see that I have an x in the domain inequality and I have a y in the range inequality. Because all the y's that I'm using live between -3 and 4. Is this a function? What do you think? Well, let's erase all of our domain and range sketch stuff and apply the vertical line test. We're good. We're good. We're good. How about over here? Oh, there's not even a function there. That's okay. Yep, we're good. The vertical line test is a winner because we never went through our function more than one time. So, yep, it's a function. That's number 15. It'll get easier, I promise. Okay, here's number 16. What is the domain? Well, this thing, was I using any x's over here? Oh, there's arrows. That means that it's going to keep going. Like, yeah, it's never going to stop. These arrows mean that it keeps going forever and ever and ever. So is there a value for like when x is -10? Yeah, it'd be down here somewhere. How about when x is -20, like way over here? Yeah, it'd still be down there. There are values for all the x's you can think of. Well, how do we write that? You get a couple of choices. All the x's you can think of would be pretty much all real numbers. So guess what? I will let you write it as all real numbers. That's how we've discussed how to write all real numbers. There's another way you could talk about this. Well, my domain is the set of x's such that I started using x's way back at -infinity. And I am going to run out of room. We are. Now I got craziness going on. I'm just going to move it over. Okay, so I'll write the little fancy all real numbers right there. Or, here's our other choice. I started using x's way back before time began, at -infinity. And all the x's I'm using are going to be between that and positive infinity. So this crazy thing that I just wrote here is the same as saying all real numbers. That's just another way of saying it's set builder notation to say all real numbers. Can you think of a number that's not between negative infinity and infinity? I can't. Okay, so let's just, there's a fast way to write that and a long way to write that. Okay, so then what's my range? Well, let's see. Did I use a negative down here? Yeah, my function would have eventually crossed there. I'm using all of my y values too because of those arrows. They just keep going forever and ever in both directions. So my range is going to be from negative infinity all the y's to infinity because range is the y is the range. It's also all real numbers, so I could have said all real numbers for this one as well. The range is all real numbers or from negative infinity to infinity or all the y's between negative infinity and infinity. Is it a function? Yes. That passes the vertical line test with flying colors. Woo, we're getting near the end. Okay, 17. What kind of crazy function is this? It's called a piecewise function because it's in pieces. So we can still write the domain. Well, what x values am I using? Did I use any over here? No. Bam! I started seeing black function. That's when I first ran into it. Well, what are the coordinates of the point where I first started to see function? It was at -4, -1. That's the coordinates of that point. But I'm doing domain, so I don't care about the y value right now. I just want to know domain. So my domain, oh, that was genius. Domain is a set of all the numbers starting at -4. That is the first time I've encountered my function. Now, I kept using function. What happens right here at -2? Well, that's an empty circle, so I don't have function. But then I have a solid circle, so I do have functions. Well, that's okay. Then I just keep using it, and oh, it's going to go out forever. See that arrow? It's going to keep going out to the right forever. Okay, how can I write that? With my inequalities, I can say that I started at -4, and the x is going to keep going forever to infinity. So this is saying all the x's between -4 and infinity. There's another way to write that. Another way of writing that is saying that my domain is the set of all the x's where x is greater than or equal to -4. Those two things are the same. This and this are two different ways of saying the same thing. I don't care which way you use. You could just always know, oh, if I always want to use this compound inequality to do my domain, the smallest number will be on the left, the larger number will be on the right, and x will be in the middle for domain, and y will be in the middle for range. That's fine if you just don't want to have to think about it. But if you get what we're saying here and you're like, oh, well, I started at -4, but then all the x's, it just kept going forever and ever. So it's just everything greater than or equal to -4. That's fine too. I don't care either way, though, which one you want. So now let's do our range. What y values are we using? I don't know. We can't see. Mrs. Bagley, you made such a mess. Okay, so turn your pencil horizontally. Am I using any y values down here? No. I still haven't seen the function. It's like, I don't know, I'm scanning. Function, no. Beep! I hit my function. And how long will I be crossing a function if I draw these horizontal lines like this? Beep! I stop right there. I no longer have function. So that means that my y values for my function start at my range. The first time I started seeing function was right here at this point. Well, what's the location of that point? That is at, well, we already did this one, -4, -1. But before, we were interested in the x value because we were doing the domain. This time, we're not interested in the x value. We're interested in the y value because we're doing range. So the first time I've encountered my function was at -1 on the y's. And since there's a big solid dot there, we're going to put an equal to underneath there. And this is range, so we got to say y is the range. And when does it stop? Well, let's see. It kept going B until there. And what's the location of that point? Well, that's up where it's on the line where y is 5. But it doesn't equal 5 because it has that big empty circle there. So that means you went right up to where y is 5, but not including where y equals 5. That's your range for number 17. Is this a function? Yes, it is. Because the only place where we were in danger of failing the vertical line test is right here. And the open, that kind of missed. That's better. The open circle says, no, we're not touching right there. And then it kind of jumps down and picks it up again. And so this still is a function because of the open circle, closed circle concept. You're like, not here, but down here. Okay. Last one of the domain and range that I'm going to do. I think maybe, no, I do 19 also. Okay, arrows. When the arrows keep going on both directions like that, it's your favorite. It's your friend. This thing is going to keep going forever and ever, forever and ever. So even though it's going up and down, am I ever going to be able to plug in like a 100? Is there going to be a value for 100? Sure. This is going to keep going in both directions. So that means that your domain is all the real numbers. And what's another way that we have been writing that? The smallest value would be at negative infinity, and the largest value would be up at infinity, and you can't actually equal those two values, so we're just going to say less than. And another way to read this is that x is between negative infinity and infinity. For your range, the range is also all the real numbers because this thing is going to keep going forever. I'm going to hit all the y's forever and ever and ever. So the range is also all real numbers, but I have to write it with, that's a negative, a y when I put it into the set builder notation. And that's an infinity, and for some reason my stylus is being wonky. Is this a function? You betcha. That passes the vertical line test. There's no loops or any place where the x's go two different places. Okay, number 19. The domain. When is the first time I start using x? I'm going to do it like this. No, no, no. Beep. That's all of the x's. When was my machine making noise as I scan for function? No. Beep. Okay, so my domain then is all the x's in this section right here. That's when I kept crossing into my function. This section is my domain. Well, how can I describe that section? That section started when x equals negative 4. And it kept going, x is between them, until we got to, oh, that could be like a fraction. We could say 5.5-ish. That's my domain. Now let's turn our scanning pencil, and we're going to scan for the y's. So I'll do it with a pointer. Where am I seeing function? Beep. Okay, let's do it again. No, no, no. Beep. So I scanned and I encountered my function in between here. When I'm talking about the horizontal lines for the y's, that's when my scanner was making noise. It was in between there. So let's describe that section. The range is going to be the first time we encountered the function was down here at negative 2. Y for the range. And the last time we encountered the function was up here at 4. And I think we could assume that it's actually touching those, so we could put the equals on there. Is this a function, yes or no? Well, if I erase all my scratch marks and I apply the vertical line test, right, that is a big fat no. My vertical line has crossed through the function twice, and so no, an oval or an ellipse is not a function. Okay, let's practice again using our function notation at the bottom of the page. So for number 20, it says if f of x equals 3x plus 2, find f of 4. So take the function f and replace the variable with 4. The input is 4. Okay, that means that instead of the variable, I have a 4. Now let's figure out what that's going to equal. 12 plus 2 is 14. So you could report back to me and say that f of 4 equals 14. When I plugged in a 4, I got out a 14. Input was 4, output was 14. So then on number 22, I think you could figure out 21, but on number 22, now it's asking you to take the function f and evaluate it when the variable is 2, and then, when you're done, add 1. Okay, gotcha. Take the function f and replace my variable with 2. And so that is the function f where my variable has been replaced with a 2. 3 times 2 plus 2. Remember, here's my function. I'm just replacing the variable with a 2. So I've done that, but then it says when you're finished with all of that, the f of 2 part, then add 1. So I got to add another 1 on the end of it. Sometimes it gives you additional instructions. Okay, so those are all my instructions. Now I just got to figure out what that is. That's going to be 6 plus 2 plus 1, which is 9. So when I evaluate the function f at 2 and then add 1, I'm getting out a 9. You can use that on 23. First, find the function g evaluated at a 2, then evaluate the function f at 5, then add those two answers together. That's your additional instructions. Okay, I know this has been an hour of functions. It's long, but it's very important that you understand this stuff. So please come see me if you still have questions.